In this lecture, I will be proving some theorems to you in circular Euclidean geometry. In whichever way it is known to you. Know this. In order to learn this type of geometry, do not rely on theorems, but learn to prove. Here, we want to prove a theorem which states that the angle in a semicircle is 90 degrees. Let's get started by joining angle A to the center of the circle. Take the radii into consideration. Each triangle becomes isosceles triangle since they have equal sides. And don't forget that the base angles are also equal. If the angle at ABO is equal to x, then the angle at BAO is also equal to x. This same idea also works for angles OAC and ACO when taken as y. Remember that the sum of the angles in a triangle ABC is equal to 180 degrees. Since we already have A as x plus y, B as x, and C as y. Now, we have to substitute the values into the expression by replacing A with x plus y, B with x, and C with y, while we equate it to 180 degrees and simplify. Follow the procedure keenly. A plus B plus C becomes x plus y plus x plus y, which simplifies down to 2x plus 2y. And factorizes as 2 times x plus y. Do not forget that A plus B plus C is equal to 180 degrees. Now we have 2 times x plus y equal to 180 degrees. Divide both sides by 2. Do not forget that A plus B plus C is equal to 180 degrees. Now we have 2 times x plus y equal to 180 degrees. Divide both sides by 2. And the result becomes x plus y equals 90 degrees. Don't forget that A is equal to x plus y. Since x plus y is equal to 90 degrees, that is equal to 90 degrees. And the proof is complete. Note that the theorem can also be proved in another way. This is something we will still do on the long run. Theorem statement. The angle subtended at the center of a circle is twice the angle subtended at the circumference of the circle. We need to prove this. Let us start by joining points BC and also point A to the center of the circle. We see that the radius remains the same in the 3 directions. Let angle OA be equal to x and OAC equal to y. We see that the triangles are isosceles. And by convention, we input the values of x and y in the appropriate sides. From here, we can cheaply calculate the third angle in each of the triangles. For the first, we have 180 minus 2x. Also for the second, we have 180 minus 2y. To calculate the third side of the angle at that point, we just need to subtract the sum of the 2 sides we have from 360 degrees. Of course, this is a variant of our basic algebra. Thus, we have 360 minus 180 minus 2x plus 180 minus 2y. By simplification, we have 2x plus 2y, which is equal to 2 times x plus y. Notice that angle A, which is the angle at the circumference, is equal to x plus y, and the angle at the center is equal to 2 times x plus y. By replacing x plus y with ℏ, we see that the angle at the circumference is ℏ. And for the angle at the center, we have 2 times x plus y, which takes 2ℏ. Therefore, we can conclude that the angle subtended at the center of a circle is twice the angle subtended at the circumference, and the proof is complete. Theorem statement: the sum of opposite angles of a cyclic quadrilateral is equal to 180 degrees. Let's start with a well-labeled diagram, and let's join the sides B and D to the center of the circle. The previous theorem which we proved shows the angle subtended at the center of a circle is twice the angle subtended at the circumference. Therefore, we have the following by convention. Just after that, we need to consider the fact that the angle at the point is 360 degrees. Since 2x and 2y form a circle, we can easily write an expression for that. 2x plus 2y equals 360 degrees, which simplifies down to x plus y equals 180 degrees. Now we see that opposite angles and C sum up to 180 degrees. Since the sum of the angles in a quadrilateral is equal to 360 degrees, we realize that the other two angles also sum up to 180 degrees. So by convention, 180 degree plus 180 degree is equal to 360 degree. Thus, the opposite angles sum up to 180 degree in a cyclic quadrilateral. And the proof is complete. The theorem states that for any circle, the angle formed between the tangent and the chord through the point of contact of the tangent is equal to the angle formed by the chord in the alternate segment. The tangent chord theorem is also known as the alternate segment theorem. To prove this theorem, let's start by joining the center of the triangle to the extremes. Let the sides of the triangle be labeled as A, B and C. The radii remain constant. Don't forget that the angle produced by a tangent to a radius is 90 degrees, therefore each side of angle C is 90 degrees. With this idea, we can write out the expression for angle BCO and OCA in terms of x and y. For OCB, we have 90 minus x, which is equal to OBC, because triangle OCB is an isosceles triangle. Hence, we input the values into the diagram. Same method applies to triangle OAC. With the expression we now have for the mini triangles, we can easily calculate the angles associated with the center of the circle. COB is thus equal to 2x. Also, OC is equal to 2y. By using the idea of angles around a point, we get the third angle, that is angle AOB, as 360 minus 2x minus 2y. After that, we need to calculate the base angles of triangle AOB. The steps above follow by convention. Angle AOB is equal to angle AOC, and both are equal to x plus y minus 90 degrees. Now, we have that the whole of angle A is equal to 90 minus y plus x plus y minus 90, and it simplifies down to x. Also, angle B is equal to 90 minus x plus y minus 90, which simplifies down to y. Now, we have angle A to be x and angle B to be y. This validates the statement of the tangent chord theorem. And the proof is complete. Properties of a rectangle inscribed in a circle and the z-angle. Consider a triangle inscribed in a circle with sides A, B, C and D. Connect the sides to the center of the circle, since the radius is any straight line running from the center to the circumference of a circle. Each length is a radius, denoted by r. For some reasons, let angle AOB equal theta. Since opposite angles are equal, we see that angle DOC is also equal to theta. Since triangle AOB and DOC have most of their properties alike, we can conclude that they are similar triangles and they are equal. Angle AOD and angle BOC also follows. Each is equal to 180 minus theta. Triangle AOB is an isosceles triangle, therefore, we derive the base angles by taking 180 minus theta over 2. The same value befall other equal angles, which were stated earlier. To complete the angles in the rectangle, we just need to work with the known sides of the isosceles triangle. Just as triangle AOB and DOC are equal, we also see that triangle AOD and BOC are equal. The angle in each of the sides is equal to theta over 2. Don't also forget that a rectangle is made up of a pair of parallel sides, one of which is line AB and DC. From this parallel property of line AB and DC, we can deduce a theorem called the 𝐶-angle theorem. This theorem states that the angles formed between two parallel lines are equal. The properties of the angles in the rectangle just validate the 𝐶-angle theorem. The line through ABDC forms Z, and the angles included are equal. This validates the 𝐶-angle properties.